Welcome to Mechanics of Composites Materials. We'll be now covering again a continuation of the topic of manufacturing processes of polymer matrix composites. And the idea there is to gain a further understanding of the things that could occur during the curing process. And we talked about how important um, uh, uh, selecting the correct cure schedule um, can impact the end result or the end manufacturing result of that composite. We talked about the kinds of material properties we can track to better understand the key parameters that drive the strength of the composites. For example, glass transition temperature can tell us a lot about the composite. And a lot of these measurements really measure properties of the resin in some cases. In some cases, it measures the strength of the composite as a whole. Um, but in general, we've made good progress in that topic. And then we talked about the errors that could occur during the pre-preg layup and the cure procedures. Generally speaking, you're going to have a number of issues during a particular processing step. And these defects can occur in large scale manufacturing as well as small scale manufacturing, and they need to be considered when you're when you're actually completing an assessment. And anytime you have issues with composites that are quite significant, that's going to cost money. Anytime you have a defect in a composite that can be quite critical, that was not qualified, you didn't qualify the system for it, which can happen. That can happen quite a bit. In those cases, you have to take action and you have to come up with approaches to then assess it. And that may mean doing more testing, that may mean doing more analyses. It can be a lot of things like that. So, I really encourage you to look at the potential problems you could have in manufacturing and then plan ahead in your qualification test program, the qualification testing that you will do to qualify the composite system. You can then look at those limits and try to incorporate these extremes that could occur in manufacturing into your qualification test program. So then when those things occur, you then can disposition them once those issues arise in real life scenarios. So that's one of the areas that I think emphasis can be placed, is to really understand the kinds of issues that can happen. And I'll show you some of those later on. So let's look at case study number one. We have an epoxy fiber composite, T300. T300 is a fiber system, and 35016 is a part is the epoxy part that we're talking about there. And in this scenario, what we're looking at now is that the part is removed from the autoclave, and it is supposed to be a 25 mil uniply. And when I say 5 mil, what I really mean is 0.005 inches. Unidirectional, meaning the plies are running in one. Basically, you have fibers only running in one direction. That's what a uniply is really talking about there. And then you have a balanced laminate, which I'll discuss later what a balanced laminate is. But what is important is that what you see here is a stacking sequence. And what I mean with stacking sequence is this tells you how the composite is built. So the first number is plus 45, and that goes against the tool. So if I call this the tool, here at the bottom, the tooling, the metal tooling, for example, then that plus 45 goes right there at the bottom. Then I put a 90-degree ply above, then a minus 45, and so forth. I stack it up all the way up to 45 here, and then I have S, which means symmetric. So this stacking sequence here is repeated above the symmetry line, and it's going to be symmetric about the mid surface. And you can see here the ply angles are shown on the right-hand side, plus 4590, minus 45.0, plus 4590, minus 45.0, 0, plus 45, and then that's a symmetry line. And then now I take this and mirror it, so that I have minus 45, 0, 0, minus 45, 90, plus 45, 0, minus 45, 90, plus 45. So that's what we got. And we call that a balanced laminate. However, rather than being a flat plate, the plate is warped. And so the question is, what is the problem? How do we verify what occurred? And what test you can perform? So most likely, what could have happened? This is what I wanted. This is a laminate I want, and they came out warped. So there's few things that could have gone wrong. A, there's a wrong layup. That's one possibility. B, there's missing plies that makes it no longer balanced. C, there's an additional ply included. Those are potential scenarios. So one thing you could do, there's supposed to be 20 of 5 mil plies. So one thing you could do is to verify the thickness, right? So each ply is about 5 ply. So if the expected thickness is greater, then you can check it, right? So you can then check the total thickness as one possibility. Check the ply thickness of each ply to make sure it got to the 5 mil that we talked about, and figure it out from there. You can then, another option is to mount and polish a cross section of the composite. You can take a cross section of the composite, look at that, and then you can do a count of plies. So here I can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20 plies. So it looks like I do have 20 plies in this example. And you can then check the orientation. You can see if that is correct. And so 0 and 90 are easy to identify. Typically zeros you can be able to see quickly, 90s you can see quickly. Other ply angles may be a little bit harder. And a high mag photo will verify orientation of each fiber implied by the oval ratio of height to width. So you can check, for example, this diameter of carbon fiber. You can check the height to width ratio. Fibers appear as ovals because they were cut at an angle to the 0 degree direction. And so that's going to tell you, hey, something else is going on. For example, here, if I look at minus 45 here, and that's 0, and that's plus 45, you can see that 0 degree plies, the fibers look perfectly circular. But when I look at the plus 45, you can see they're oval. So you can use geometry to determine, oh, okay, so is this, the height to width ratio is this much, so the fiber should be oriented at a particular angle. And so you can get that information very quickly. The wider the angle is, the more the ply is oriented away from the 0 degree, the more ovalized it's going to look like. And that makes sense because if I'm doing a very extreme cut, say I'm cutting a 90 degree ply, I'm basically cutting along the whole length of the fiber. So I should be able to see a very long oval, if you will. So that's one approach you can use for case study number 1 as an example. Yeah, so for those that are watching this, there's an error that put here on purpose. So here it was supposed to be symmetric with the S. That's what symmetric means. And I hope you caught it and you can see that. And the error is that it's supposed to be mirrored by 45. And you can see here that it's not mirrored by 45 because there's a minus 45. So for it to be perfectly symmetric, you need to have these at 45 as well. And that says minus 45. So that's an error that was also caught by this cross-sectional work that was done. Now, looking at the fiber systems, I've talked about how many different fiber systems you can have. T300 is here, what you see is a T300. And T300 is a fiber produced by Toray, which is a company that's called Toray Composite Materials America, Inc. And typically, this kind of fiber system tends to be very high modulus fibers. And the baseline is a very nice carbon fiber. It's a baseline carbon fiber that is using aerospace applications and has a lot of history, over 20 years, and has even over 30-year production history. And it is known for having a really nice balanced composite properties. It's very consistent, it's reliable, and also is available in a lot of different toes. For example, you can have 1,000 toes, 3,000 toes, 6,000 toes, even 12,000 toes. And with that said, there's other material systems like T700 and so forth. The T300, just for your information, comes with a tensile modulus typically of 33 MSI and usually has really nice tensile strength. You also then have epoxy, which is what you see there that I'm showing here is 3501 6. And so you have to then understand a little bit better what that is, and you can look at Hexcel. For example, that product is a potential product you can purchase from Hexcel as a possibility. Not always, but you can. So certain products can be purchased from different places. The bottom line is that the 35016, which you're seeing there, is really a high strength, damage resistant structural epoxy matrix. That's why it's so nice, because it's an epoxy resin system that can be either used with unidirectional woven composites even. But the nice thing about 35016, it was developed to operate in an environment up to 300 degrees F, which is really nice because you may have a lot of applications where composites could be exposed to high temperatures. What is interesting is that the TG, if you're measuring it dry, because remember, I told you already that the resin can change behavior if there's moisture or not. So the glass transition temperature at the 6 hour time mark at 300 degrees F, dry is going to be about 410 degrees. And when you look at wet, the temperature drops, the glass transition temperature drop with a fixed temperature of 300 degrees F down to 300 degrees F. But yeah, you can find this kind of spec and look at that and understand what it offers in terms of shelf life, storage, how it needs to be stored, how it needs to be shipped, how it should dispose of any scrap. So for example, if I want to dispose of 35016, in this case, for this material, the disposal of this material should be in a landfill in accordance to whatever the regulators say. And so, yeah, it can be landfill, but it needs to follow a particular approach, okay? So that was just an example, just like a case study to show you what could go wrong. In this case, it came out warped because one of the ply angles was wrong. It was not plus 45. And so that's why I find this case study exciting. So let's look at case study 2. We've asked you to manufacture a 10-ply unidirectional composite utilizing a T300 fiber with a RS3C cyanide ester on a graphite mandrel. So now your tooling is going to be a graphite material, which has its benefits because when you go to very hot temperatures, graphite does very well, and there's a low CTE, low coefficient of thermal expansion. So you may have lower residual stresses as a consequence. And so the composite looks like it has blisters on the surface, and we're wondering why that is, why that issue showed up. And so why don't take a minute and maybe 10 seconds and think about it, and let's see if you have some ideas. So now that you kind of paused and thought about it, let's see why. And before I hit that why, I already discussed what T300 fiber is. Let me talk about RS3C cyanide ester before I go into the answer why these blisters occur on the surface after curing. So 3S, you're going to see RS3C cyanide ester, and pardon me if I'm going into too much detail, but I think it's worth kind of showing you the different composites you could have and what you may use in different applications. So the RS3 is a very well-known resin system. It's a cyanide ester resin that has been developed by, again, Toray as a potential option of procurement, and it's developed to provide a good balance between toughness and high temperature wet performance. The RS3C, you're going to see that used a lot in areas such as satellite, aircraft, missile applications, and dielectric structures. The RS3 comes in a lot of different formulations, and they're also available in extreme low flow autoclave versions of that. There is industry standard Prepreg system for satellite applications, And the benefits is the low dielectric constant and loss. Some of the markets where you may see the RS3C being used is the radome, the space and satellite sector, and it does come in a thermoset prepreg. You're gonna see Santa Esther with a TG typically, 177 at 350 F Fahrenheit, and on this one you're gonna see a out life of about 30 days. You can also do a post cure if needed, but typically that might not be necessary. So now looking at going back now to the question is the first thing we want to check is do we cure the composite properly? We need to figure out, is there an error in what we did? So in order to do this, we need to perform a DMA, a dynamic mechanical analysis to determine TG. And I already showed you earlier, and you already watched videos on DMA testing to determine the glass transition temperature. And you can then determine that by looking at the loss of modulus curve as a function of temperature. And we know for this system that the resin, when cured to 177 C, should give you a TG of about 195 C. About that, okay? Okay, so we also know that the fiber should not be affecting or contributing to the TG of the composite. So then I go to the DMA and we have identified that TG is lower than expected. And it's the most likely contribution to the low strength we have. However, this may also just be something that we may not be aware of, like some other factor. Maybe it's due to the sample not being exposed to the correct thermal uppermost temperature, maybe something else. So we then post-cure the sample at the highest temperature and run another DMA to verify if the TG increases to 195 C. But it doesn't increase to those values. So it was not this other thing we thought about. It is most likely in this case a carbate formation. Once we identify there's carbate formation, we have to then identify the source for that moisture because we already talked about how moisture can contribute to carbate formation. And carbate formation is one of the things that could occur in composites when there is carbamate formation, when you have moisture present, okay? And so that does happen in cyanide ester, and it needs to be accounted for, okay? And that's somewhat of a progressive thermal degradation that can occur due to that and has to be looked at carefully because it can lead to low strength reduction. Mandrel, we look more carefully and we find that the mandrel actually, the tooling, and let me remind you what I mean with tooling. Okay, we talked about it earlier, but I think it's worth kind of reminding you one more time. So this is your tooling, this is your mandrel, this is your mold, this is where you stack stuff up. So when I say mandrel, tooling, mold, that's what I'm talking about. I'm talking about the tooling side. That side is made of graphite in the example we're talking about. So the mandrel appears to be the culprit, and if so, the plies adjacent to the mandrel should be more degraded than those away from the laminate. And when we verify that through an image analysis of the cross-section, we find that in fact, there is some damage going on the mandrel side, and there's blisters that are forming due to the decomposition of carbamates to CO2. So that's what's going on there. That was a forensic analysis in 2 minutes. That's what we've done. But again, anytime you fabricate a composite and you see some sources of issues, I think the idea there is to understand why those issues occurred. And that's exactly what we're talking about here, how you perform those forensics in a smart way to get to the answer that you want. Case study 3. So let's look at case study 3 and let's do the same exercise. So looking at this, you receive a T300 epoxy unidirectional prepreg for a build that is already running behind schedule. So we already have an issue there. We don't understand what's going on 100%, but we do know we're running behind schedule. The prepreg appears to be fine and meets all your tests, but during autoclave, the part overshoots the final cure temperature by 50 C, which is not a lot, but it can happen. And you wonder why. So, okay, that happens. So the 175 versus 125. The part is going to be used for a cryogenic pressure vessel that experiences a temperature swing from plus 120 to LH2 temperatures, cold temperatures. Your boss, which in this case is me, wants to know if the part will be fine. What should you do? Can you think about it before I continue? So why you don't pause for a couple of minutes, think about it, and tell me what you think we could be doing. Okay, now that I think you thought about it, um, so we overshoot the third stage or uppermost cure temperature. Uh, Typically, it shouldn't affect porosity. We talked about it in that third stage. We shouldn't be seeing that, but it may affect the degree of cure of the resin. So you decide to perform then a DMA measurement test, which I think is a good choice to look at that. And we measured a TG of 200C instead of 145C. So that is a significant increase and may decrease the failure strain. It can become more brittle if that happens and increase the modulus of the matrix material. The tank needs to not allow permeability of liquids and gases because it's going to be used in a pressure vessel, which is pressurized. So we recommend then to thermally cycle the test specimens and measure mechanical properties using mechanical tests with this higher cure state to verify if any of the material properties of the composites were compromised compared to one that will have had the correct cure. So in other words, you run testing, mechanical and thermal testing on the correct cure, and you also do it in the incorrect cure. So you also may perform microscopy before and after thermal cycling to verify if there is extensive microcracking of the matrix, which could be a problem for this actual application because if it's pressure vessel and you have a lot of microcracks, then you can have leakage through the wall. Higher than expected cures are typically are not a problem, but in this case, it could be because of the microcracking that we're discussing. And embrittlement can be an issue. So with that said, any thoughts on that? Any questions? Why don't put it on your chat or let's discuss it now because this is a great point. It's something that could happen. Continue on the effects of defects on composite performance. Let's look at that because that's very important. And these are the kinds of defects you could have in composites that need to be considered. You have delamination. Delamination can cause catastrophic failure due to loss of interlaminar shear carrying capability. And typical acceptance criteria require that the detection of delaminations are greater than 0.25 inch. So typically, you're able to find defects of that size or larger. If it's small, it can be a little bit harder. But typical acceptance criteria, and when I say acceptance criteria is, I'm not saying it's going to be 0.25. Some people can say 1 inch. It depends on the design. But when I say acceptance criteria, what I really mean there is if there's a part that you manufactured and there's a delamination, which is a defect between two plies, and that defect occurred during manufacturing, you want to have some sort of criteria that tells the quality engineer, okay, if this defect is too large, you may want to repair it. But if this defect is less than that particular threshold that you have established, which I'm calling acceptance criteria, if it's less than that size, then you can just go ahead and use it as is with no problem. So that's what we're talking about there with acceptance criteria. Then you have the impact damage, where if you have some amount of damage that could occur because say somebody drops a tool, like a hammer onto the composite. Well, that tool that tool that you drop can cause some damage on the surface, and that's going to cause some issues there. So that can reduce the strength of the composite 80% if you can see it very easily, 65% if it's barely visible, which is crazy, but it can happen. Now, I'm not saying it's exactly 65%, I'm saying up to 65%. So it can be very small amount of loss. It doesn't have to be that much. Then you have the ply gap. Degradation depends on stacking order and location. So for example, you have a 0.4590 minus 45, and then you have it symmetric. And is a laminate. So apply gap, you're going to have a 9% strength reduction typically due to gaps in a 0-degree ply, a 17% reduction due to gaps in a 90-degree ply. So that's another issue that you could see. Ply waviness. Strength loss can be predicted by assuming loss of load carrying capability. So typically, say a ply is extremely wavy. And what I mean with that, I don't have a picture of a wavy ply, but say this ply here had waviness, meaning it went up and down, wrinklish. So that's going to cause a strength reduction. For 0-degree ply, ply waviness in a 0-degree ply, for this laminate right here, it can cause a static strength reduction of up to 10% for slight waviness, up to 25% for extreme waviness. So something to really understand. Fatigue life can be reduced by at least a factor of 10. So it can be quite dramatic. Porosity can degrade the matrix dominated properties. We already talked about porosity. Porosity can be a problem if the pressure applied to the composite is not sufficient to push the voids out. And we talked about how that's so important in those initial stages of the cure process. It can increase equilibrium moisture levels. It can aggravate thermal spike phenomena. And surface notches. Surface notches can be an issue. And thermal overexposure. So thermal overexposure can lead to matrix cracking, delamination, fiber debonding, and a permanent reduction in glass transition temperature. In other words, you can have irreversible damage there. Autoclave prepreg composite. So the advantages are that you're able to achieve a high fiber volume content with autoclave prepreg composite. And I'm talking about autoclave, not out-of-autoclave. So autoclave prepreg composite can give you high fiber volume fraction, good fiber orientation, a 0.5 to 1 degree, consistent material properties, and low porosity with autoclave. The challenges that you have with autoclave is size constraints. So anytime you need an autoclave, say I want to cure a whole airplane, well, the size can be an issue. You know, how do I do the whole thing, you know, in a super autoclave size? Cost, time consuming. You have to figure out processes to join parts. Large parts will push the limits of the prepreg out time. So say you're making a part and I have to take prepreg out so I can use it, you may need the prepreg to be out for too long, because to make a large part is going to require me to have those materials available to me during the manufacturing. You can also do some rotation approach where you are rotating materials from the freezer and taking them out and then putting them back in. But again, we talked about the cumulative time of out time can be limited and constrained due to aging issues within the composite. If anything goes wrong with resin, you know, that's a costly expense. Since the fiber is non-recoverable, that can be an issue. So size constraints and time constraints can limit the autoclave processing with the advent of larger and larger parts that you may see. Now, if we talk about out-of-autoclave processing, and here I have a PowerPoint on the left showing a system, Ares 5, that will be one of the largest composite aerospace structures ever built. And one of the primary obstacles to building large parts is the size of the autoclaves being used. Like I said, it can be limited to what you can do. And so here you can see the autoclave prepreg scenario. You have the fibers impregnated in the resin very seamlessly. And then with autoclave prepreg, you can see an evacuation channel in between. So it's a little bit different. But the autoclave processing promises to produce space-qualified composite parts without the use of autoclave pressure by utilizing partially impregnated prepregs. This partial impregnation allows gas to transport, at the early stages of the cure, And at the later temperatures, it promotes the infiltration of the resin into the drier regions for full consolidation. So again, at the early stages of the cure, you allow gas transport. And at the later temperatures, it promotes infiltration of the resin into the drier region for full consolidation. The prepreg that does not need an autoclave will yield less than 2% porosity. So comparisons of how voids formed during processing. So these are standard autoclave prepreg. These are semi-impregnated out-of-autoclave. That's your evacuation channel to allow gases to escape. And in order to aid in the removal of entrapped voids in an autoclave, prepregs many times had to be partially filled with resin to allow removal of pathways. So that's something to consider in these applications. So what are the considerations that need to be considered? You have the air entrapment. You have volatiles generated during cure. You have moisture dissolved in resin due to out-of-time exposure, Issues related to aging may shift processing window. And then you have tackiness that needs to be looked at. You have flow-induced out time and vacuum quality. So autoclave prepregs are designed to remove voids with only vacuum pressure. Autoclave prepregs rely on dissolution and compression of voids due to high pressure. So those are the areas that we want to learn more about. And semi-impregnation can help with that. Autoclave processing, so if I look at a micrograph of a composite cross-section without pressure, so here I have autoclave prepreg and here I have out-of-autoclave prepreg. So you can see a difference there. The schematics of prepreg impregnated composite materials are shown here at the top. And the distribution of resin before processing may affect the network of available pathways for air and volatile removal. So here's your laminate thickness as a function of processing time. And here you can see how as a function of temperature, the laminate thickness as a function of time. And here I'm showing the cure temperature schedule. You can see how the laminate thickness is decreasing over time. You have debulking, which is drawing vacuum using a temporary set of, after a small number of plies are laid down. You have vacuum holes, which are drawing vacuum on the final back configuration, and that's designed to extract the max amount of air prior to cure. This is a function of part size, prepreg, permeability, and can be in excess of 16 hours. So very, very interesting stuff, very, very interesting. So here again, you can see autoclave prepreg and out-of-autoclave prepreg, the differences there. Now, there's a lot of modeling that has been done. We won't do any modeling in this class on this topic, but I want to bring this topic to your attention, in case you're faced with that. But a lot of people have used the ideas from Darcy's law, which is the question here shown at the bottom here, which is a material property that describes fluid flow through a porous medium and how permeable the material is. The apparent fluid velocity can then be looked at, and it's described by Darcy's law. And it depends on the permeability material property and the fluid viscosity, and also depends on the fluid pressure. You can then apply Darcy's law to air velocity in a prepreg. You can apply these ideas to calculate what's going on, and simulations can be performed. So here's kind of like the setup of how the modeling works. I don't want to go into an extensive detail, but the point is that you can do these models to better understand whether the air is getting extracted properly. So what are the differences between out-of-autoclave and autoclave? So on the left side, you can see an autoclave cure, of course, with pressure. And the pressure is increased to about 0.5 megapascals. And then you have temperature versus time here on the right-hand side. And you can see how the temperature profile is provided, and you have this out-of-autoclave cure. So you can see it's quite different from the picture on the left. Absent of this, what you see is there's no pressure applied in addition to vacuum bag. So the autoclave prepregs have been formulated for both auto-autoclave and standard autoclave cures. The cure schedules are longer at intermediate stages, allowing more time for volatiles to be removed prior to gelation. And then that can be up to 10 hours. The final glass transition temperatures are comparable between out-of-autoclave and autoclave systems. Out-of-autoclave prepregs may also be partially infiltrated to better allow removal of volatiles at lower temperatures. So hopefully that's making sense to you. One problem that you see with autoclaves is the higher porosity and lower fiber volume content in cured laminates, and that's due to the lack of pressure, right? The lack of pressure. When you apply pressure in combination with temperature, that pressure you're applying to the part is pushing the voids out. These autoclave prepregs are often processed with interpenetrating networks that utilize both active cross-linking agents as well as latent cross-linkers. The active cross-linking agents causes cross-linking during synthesis, while the later cross-linker causes cross-linking only during the post-curing step. So yeah, that's the special consideration that we have to keep in mind. The heating due to the second dwell, so the heating to the second dwell, is critical phase for void formation, as the change in temperature causes the vapor pressure in the voids to increase, causing void growth. And we talked about that, how increasing temperature can really increase that void growth. Volatiles will grow when the resin pressure drops below the void pressure. In the vacuum only process, the resin pressure can be very low, providing ideal conditions for void formation. So in other words, when we are using autoclave, don't be surprised if the porosity is greater. So very important consideration. So how do we remove voids in an autoclave approach? In autoclave processing, there's this rheological evolution, which is critical for void removal. A high viscosity during vacuum is necessary. That allows you to retain open cell voidage so the gas that was induced can escape. Low viscosity during heat is also necessary to remove flow-induced voids. So in autoclave, there's additional factors that do really play into these issues. The initial degree of temperature cure, whether you're working with a unidirectional lamina, which is plies going only in one direction, or whether you're working with a fabric, which means plies are running in multi directions. We also have debulking during durations and dwell temperatures. All that becomes extremely important in these calculations. Okay. So here's an example of autoclave versus standard autoclave. So you have the shear strength shown here. You have the fresh and out life for these materials. Yeah, so it's kind of like a comparison. And aging really significantly increases viscosity profiles of autoclave resins and may also result in sharp increases in porosity and degradation of matrix-dominated mechanical properties. So that's one of the things we want to be paying attention to. And you can see how void content was quite significant for this autoclave process that's pointed to here. Okay. Most of these are autoclave. That was autoclave right here. It's box. That's 8.3. And you can see how that void content is larger than other applications. Okay. What are the types of defects that are observed in autoclave applications? And here's a picture that came from a paper that here illustrates the types of defects from autoclave by former professor Timothy Sintea at USC. And that was my Composites journal article, part A. And you can see you get delamination, macro voids. You can get corner thinning. So it's thinner here compared to here. And you can get also corner thickening. So these are kinds of things you could see. Autoclave processing, the advanced composite cargo aircraft fuselage comprises of 8 pieces molded from autoclave cured MTM45 prepreg, which is supplied by the Advanced Composites Group. And you can see here a fairly large piece using autoclave processing. So again, autoclave processing does offer benefits with some downsides associated with potentially more defects in the manufacturing. And then you have the automated composite processing. You have fiber placement, and then you have tape laying. Okay, so I'll go into those later, but automated composite processing is very useful. It fully automates the making of the composite and keeps it very simple using robots. Automated composite processing is in its simplest form a continuous narrow unidirectional tape, usually unidirectional, and also typically this unidirectional tape. When I say unidirectional tape in the future, I'm talking about a bunch of fibers that they're bundles, and they have impregnated resin in them, and they're wound onto a rotating mandrel. So that's what you will see. The tape or top preg is then fed via translating head with an accurately controlled fiber feed angle to the axis of the rotating mandrel. We'll see that later on. Consolidation pressure is achieved through tensioning the fibers as they are wound onto the mandrel. And with the growth of automation, this basic process is now being used to produce very complex components that are not circular necessarily, and that utilizes multi-axial robot placement, which allows for unidirectional prepreg to be placed very accurately onto the tool surface. The process is then referred to as automated fiber placement or automated tape placement. So in an automated composite processing, the things that you normally do. So for example, you have the raw material, you have to cut and kit the material, then you have to prepare the tool, and then you have the layup guide that has templates on how you're going to put the plies in with laser projection and all that, and so on. Well, the automated composite processing has removed some human aspect by removing this right here. And also you have this tool preparation eliminated to some level and layup guide. You also have a reduced number of debulk cycles due to this. And yeah, pretty much the rest is the same. And just to remind you what the typical composite processing was about, you have these raw materials, like if you were to make a cake, you have the flour, the different things that go in. With composites, we need the prepreg materials. We need the tooling, the mandrel. We need the bleeder, the breather, the film, release film. We need the vacuum bag. We need, all those are the ingredients, right? And then we cut and kit. We prepare the tools. We lay it up. So all this stuff is what you may be used to. An automatic tape layup, and I'll have a later chart on that, but here you're going to have, yeah, basically this is the prepreg plies are here, and they're getting fed in, and these are your cutters. And as you lay it down, you have local heating applied, and you also have pressure applied against the composite so that it's rolling in there with pressure. And then you have backing paper that's getting removed as well, because sometimes there's backing paper that's in there that needs to be removed. And here you can see the picture of that process. The automatic tape layup has been extensively used. The Boeing 777 has a horizontal stabilizer skin panel layup. Automatic fiber placement. Fiber placement is an automated composite manufacturing process of heating and compacting resin pre-impregnated non-metallic fibers on very complex tooling mandrels. The fibers usually will come in tows, like I talked about before. And a tow is typically a bundle of carbon fibers impregnated with epoxy resin. And usually it's going to be about 1/2 inch wide by 0.05 inch thick or 5 mils thick. and it usually comes in a spool, on a spool. The fiber placement machines generally have a capacity of 12 to 32 toes, or when placing all toes at a time in a course, have respective course widths of, can go from 1.5 to 4 inches in width. The toes are then fed into the heater, like I discussed, and a compaction roller on the fiber placement machine head. And then the robotic machine, the movements of it are the one that's actually laying the fibers down, the pre-preg down. And a lot of these machines, fiber placement machines, are going to be rated in terms of how many they can produce per hour, how many pounds of composite can produce per hour, how many pounds per minute it can do it. And that's a very critical, important aspect of this. And you can see here a picture that's zoomed in, but you see some heating going on. You can see the fiber being fed in, and you can see a roller that's applying the pressure down. And then this has several degrees of freedom, so it can rotate quite significantly. You can see here the layers being laid down and the different angles. And here's just yet another example of an application. And then the tooling can usually be a aluminum mandrel. So again, you need to lay the fibers in some surface somewhere. So aluminum mandrel is a typical one, but does have high coefficient of thermal expansion. The Invar cure tool, Invar is very expensive, but has very low coefficient of thermal expansion. So that's why I could make it a good choice for a lot of these applications. The fiber placement head, just going a little into more detail about what's in there. You have your individual toe payout, and the tension is being controlled here. You have your clamp, you have your compaction roller. You can see here the fibers getting rolled in. You have the cutters and then the control heating right here, right there, so that when it goes into the surface, it's already hot. And here's an automatic fiber placement shown here. So what's next for automatic fiber placement technology? The technology has just overcome a lot, and there was this hype cycle about it. So what is really next here? High rates of automation. We need there's need for speed. New programming and simulation tools are being used to exploit toe manipulation, fiber steering. Fiber steering is very complicated. It depends on a lot of parameters such as material tackiness, compacting the pressure of the roller, layup velocity, heating power, and vacuum bagging. Engineering for fiber steering requires the design, analysis, and assessment cycles to be integrated. Automation of inspection, that will be very helpful. If you can lay down the composite and also do an inspection process that's automated, that could be quite powerful. Artificial intelligence now with machine learning applied to the software, so it can better optimize its paths. And you can have also collaborative toe placement. And one approach is to have multiple machines. So you have multiple machines trying to place a material in the same part at the same time. But yeah, so it's done a good job. Okay, so we'll cover filament winding. Filament winding is an approach where typically you're making pressure vessels if you're going to use filament winding technology. And it will wrap continuous reinforcement of resin impregnated fibers. So you have the fibers here, the fiber spools, and the fiber spools are getting fed into the filament feed, which is then going through a resin bath. And now that the filament wind has resin impregnated in that, and the resin bath is fairly wet, it goes through this here, and now you have a mandrel that's rotating. And that fiber can now be put in at a 90-degree angle, which is hoop. It can go at 30 degrees, which is what you see there. We call that a helical angle. It could go 50 degrees, 60 degrees, and so forth. So the combination of the mandrel rotation and the actual motion of the fiber source produce the helical pattern. That's how that works. And that allows you to actually be very creative with your designs. There's not a lot of manual labor. All is going on here. There's rotating and you're putting fibers down. And that ply stacking sequence is chosen in a very particular way. But in general, you're getting that fiber being placed onto the composite very successfully. In filament winding, the filament are carefully wound onto the mandrel after being wetted with the resin. When the resin number windings is obtained, these objects will be cured. At that point, the manufactured object will then often be in cylindrical shape. Typically, that will be a cylinder. In this region, you're going to get a very, very interesting behavior towards the end, which we call polar winding. So it's going to look like that right there. Yeah, so filament winding process is a band of continuous resin impregnated filaments wrapped around a rotating mandrel and are cured to produce axisymmetric hollow parts such as automotive drive shafts, you may see them there, helicopter blades, oxygen tanks, seen them there, pipelines, spherical pressure vessels, seen them there, conical rocket motor cases, and a lot of gasoline storage tanks. The typical wind speeds are pretty nice, 300, 360 linear feet per minute. However, if you need a really precise winding, you probably want to go slower. Two types of filament winding processes that are used are called helical winding and polar winding. The winding angle, the angle of roving band with respect to the mandrel axis, that's what that is. And the winding angle ranges anywhere between 0 degrees to 90 degrees. But not exactly 0 degrees because you have to go, if it's 0 degrees, you're basically going almost horizontal, which is really hard to do when you're going particularly around this area there that I'm pointing. So we got that. The filament winding, you have here several aspects that are quite interesting. You have the property of characteristic, you have the wet winding, right? And then the prepreg winding that somebody spoke up about. So what I was discussing right now here was wet winding. And now what I'm talking about is that you can do similar things with prepreg winding, which is what one of you inquired in the chat, or I can't remember. But you have the property of characteristic, and in this case it's liquid resin, in this case it's B-stage cured, which means it has cured some amount. You have cost involved here, and the wet winding provides the lowest cost, while prepreg is a lot more expensive. Resin formulation, you have a bunch of them, but here you can do so many proprietary formulations. Viscosity is low here. Here you require, with prepreg, you require high level of compaction. Resin content control, it can be variable here, but with prepreg is well controlled. You also have room temperature cure, which is possible with thermal wet winding. And then you also have, room temperature cure, you can do it with this. Heat cure is required here. The storage can be a problem with prepregs. It requires storage that's in freezing temperatures, while you can have longer shelf lives with filament wet winding. Winding speed can be fairly low to moderate, while here it can go to high. The design database is a lot with wet winding. So if you're wondering which one I select, I'll say wet winding is typically the approach you want to go with. If you can afford the cost and you can afford other things, maybe the prepreg winding. But remember, you have that out time issue, the freezer storage issues. So the wet winding is not very clean compared to the prepreg, and scrap rates tend to be moderate to high with wet winding, which is lower with prepreg. Compaction requirements, you don't need any compaction with wet winding. You're achieving that with the tension on the fiber that has been wetted. And then here you do need some amount. And then quality assurance needs to be implemented. But yeah, those tend to be the things to consider. The tool around which the impregnated roving is wrapped is the mandrel. And the mandrel can be a lot of different things. People have used soluble sand mandrels. So let me explain what's going on. Say I totally wrap this thing, totally wrap it, 100%. How do I remove the tooling from the bottom? How do I pause it right now? Think about it. Pause your mind and think about what I'm saying. I'm wrapping this system completely filament wound. How do I remove the mandrel that's been wrapped around? Yeah, I mean, one approach is to use plaster, soluble sand mandrels. You can use collapsible mandrels, tube mandrels, ways that you can remove it. Waterable soluble mandrels are used for rocket motors, but you could have metal as well, but you may have to cut it. You may have to cut this and somehow join it in some other way later. But yeah, those are some of the issues with filament winding. It adds additional steps. Like how you remove the mandrel. And if you have to remove the mandrel, perhaps you have to come up with a unique solution for that application that I cannot say because there's so many ways of probably doing it. So mandrels and tooling, I already talked about plaster, collapsible, non-reusable foam. And these are the applications where you can use them. Spherical tank, pressure vessel, aircraft wing and flap. In filament winding, the process parameters are going to be the fiber tension, the fiber wear out, and resin content. Fiber tension is created by pulling the roving through a number of fiber guides placed between the crills and the resin bath. Fiber tension occurs by maintaining the fiber alignment on the mandrel and to control resin content in the wound part. Excessive fiber tension can cause differences in resin content in the inner and outer layers, something to keep in mind. And you could have even fiber wrinkles and undesirable residual stresses in fiber breakage, even from that initial manufacturing. Fiber wet out is really nice. It reduces voids. It can be controlled by viscosity of the catalyzed resin in the resin bath. There's a number of strands in the roving which determine the accessibility of resin to each of the strands. Fiber tension, which controls the pressure on various layers already wound around the mandrel, and then finally speed of the winding and length of the resin bath. These are the main factors driving speed. And also main factors for reducing voids as well. So viscosity keeps coming up as a topic. Just remember that. These are the common defects you may have in filament wound parts: voids, delaminations, fiber wrinkles. Voids typically appear when you have poor fiber wet out, and there's air bubbles in the resin bath, and there's improper bathing. And so the bandwidth will result in gapping or overlapping. And then you have delaminations that are due to excessive time lapse between two consecutive layers of winding, especially if the resin has a limited pot life. Meaning, I did one layer one day and then a layer like in 2 days. Well, you may have issues there. Reducing the time lapse and brushing the one layer with a fresh resin should be done before the next winding to reduce delaminations. Wrinkles result a lot from improper winding tension and misaligned voids, rovings. Unstable fiber paths that can cause fibers to slip on the mandrel may cause fibers to bunch and bridge and improperly orient in the wound part. So when I compare filament winding with fiber placement, they look similar, but there's main differences, right? So on the left, on the filament windings technology, you can control typically a thing called filament winding technology. On the right-hand side, you're going to hear fiber placement, automated toe placement, and automated fiber placement. So those are the terminologies you may hear. Now I go to mandrel. It requires forming mandrel of some sort that you can take out. With fiber placement, it requires forming a mandrel of some sort, but you can take it out easily. You have resin application state. The resin may form maybe wet resin bath or wet resin bath with drum. Prepreg resin or fiber form you need that. and then you need dry fiber only, no resin. So on the right-hand side, resin must be a prepreg for it to work. Then you have the fiber forms. The fiber forms comes only in prepreg form, some of them. So I've shown it here in the right for that, for fiber placement. On the left side, where I'm looking at filament winding, you can have a lot of different forms of fibers, including individual rovings, individual toes. It may be that you have a number of rovings or toes to expedite the problem, and you also have tape, which may also be the selected, maybe the selected form. More and more parameters. We have fiber tension. The fiber rovings or toes are continuously under tension during the winding process and are not cut until winding typically is completed. While on the right side, you have rovings or toes that are not under tension, but are placed onto the surface and are compacted by that normal pressure we talked about. So that's important via the roller, right, that we talked about. And it relies on the tackiness of the toes the toe that's bundled to tack, to stick. Cutting fibers are usually not cut during the process into the filament winding technology and are not added during the winding process. But you may need to do that on the right-hand side, which is the fiber placement technology. Fiber or torque steering, the fiber are always tension and take up part of the path of least resistance, unless they're trapped in some sort of issue where it's not allowed, the design is not such that you can do that. With fiber replacement technology, fiber toes and bends may be steered along different paths and angles on the surface since they're not tensioned like those used in filament winding technologies. And I'll skip resin fiber temperature. Feel free to kind of pause and look at this carefully. I'm going to keep moving on because, so here in this case, you have a prepreg fiber that's warmed up. And here in this case, you have your out-of-fiber placement technology. Again, filament winding versus fiber placement, you can work with many more resins compared to the proven approaches in the resin industry with automated fiber placement. Typically, you're using epoxies, BMI, and a number of thermoplastics. We also have resin transfer molding, which is a low-pressure closed molding process, which offers a dimensional accurate and high-quality surface. Really nice. And it uses liquid thermoset polymers reinforced with various forms of fiber reinforcements. Typically, polymers of epoxy, vinyl ester, methyl methacrylate, polyester, or phenolic are used with fiberglass and reinforcements. Other reinforcements are offered for more demanding applications such as aramid and carbon. And the metric selection for polymer and reinforcements typically will dictate both the material modeling, the model cost, the molding cost, as well as molding mechanical and surface finish performance. And here you have an example of an RTM. You have the molds, the composite system in here, and now you press it in there with pressure, and then you have a cure agent and the resin being injected, and now you have your finished part. I apologize for that. You have the resin transfer molding. And here what I'm showing is a more zoomed in view of this. You have a reinforcement placed between two parts of mold. The resin is injected into the mold and the heat is applied. Advantages, accurate molded surfaces. Another one is coherent reduced part count. Disadvantage, low fiber volume, low, and also you're gonna have material property variations throughout the part, and high labor is another issue you're gonna see. You have textile preforms for RTM. You can see track-sleeve braided composites typically, rhythm shapes. You can do a lot of complicated things with RTM. Resin transfer molding. You have textile preforms. Here's an example of the kinds that you do. Yeah, so these are your different textile preforms that you can use for making composites. You have the 3D fiber preforms that you're going to see a lot. You have the angle interlock here. You have the angle intertalk with separate layers, and then you have the profile orthogonal. So resin transfer molding refers to a group of processes that inject resin into fiber preform placed in a closed mold or tool. The resin injection point is usually at the lowest point of the mold cavity. The injection pressure is in the range of 10 to 100 psi. And as the resin spreads throughout the mold, it displaces the entrapped air through air vents and impregnates the fiber preform. Starting preform for RTM needs to have the shape of the desired product. Preforms can be made by a variety of textile composites processes such as 2D and 3D weaving, braiding, and stitching. Woven for non-woven preforms may be stamped or formed to shape. The resin reaction may be initiated by heating or by mixing or reacting compound prior to injection. So, yeah, both important things that need to be considered. RTM variables. So just like with filament wine technology, I discussed the variables really quickly. RTM variables include pressure, which determines the mold material requirements. Relatively high pressure is needed, greater than 50 psi for RTM. And again, just to remind you what RTM looks like, it looks like this. You have two pieces compressing into the part that you want to make. So here you can see another example, and you push in to get the design out. Temperature, it depends upon the resin system cure cycle and minimum viscosity. The viscosity of the resin during infusion is a major component in determining both pressure and temperature requirements. Fiber content, the maximum viscosity allowable for RTM depends on the fiber content, which can be 50, 70%, and so forth. Fiber orientation, the fiber angle in the preform is relative to the flow path of the injection and affects the resin flow velocity and the wear out of the fibers. And finally, part thickness. This may have a bigger effect on fiber wear out and void content of the molded part. So again, pressure helps with some of this. So RTM variables, the advantages, you can make very complex shapes efficiently and cheap. Production time is way fast. Surface finish is great. You also have net shed parts with minimum trimming and potentially cost effective for mass production. So definitely something to look at and spend some research funding into that. RTM can produce really high volume at low cost in the automotive industry, as well as higher tier companies in the aerospace industry. Moreover, RTM is really suitable for making very complex composite parts. Yeah, so that's the advantage there. And then here you have the vacuum assistant RTM. Again, the idea there is to try to remove any voids. Yeah, so that's an advantage there. So here compare RTM and vacuum assisted RTM basically. Yeah, so I just listed here, but yeah, so yeah, there's no size limitation with VARTM. But other than that, very similar. VIA RTM, processing for aerospace components. Yeah, it's repeatable, has been automated, has been toughened to get the right resin behavior and formulations that you need. Compression molding is another technology. Yeah, so compression molding is is used a lot also. It's used for transforming sheet molding compounds into the finished product. The advantage on this one is the ability to produce very complex geometry in short period of time. So I already covered this. Basically, is what I talked about before. And here is a machine that can do that. Compression molding also requires similar to materials to what we discussed before. The compression molding cycle time can be 1 to 4 minutes. I do want to remind people that you have your materials as your step one. Step two is compression molding, step two there. Step three is thermoset resins in mold cure, no cure for thermoplastic resin. So here's where you start curing things. Sheet molding compound is another technology that's used. SMC is a combination of chopped glass strands and filled polyester resin in the form of the sheet. And the prepreg will contain some of the components mixed in. It's going to have resin, reinforcements, feeder, catalyst, and so forth. Sheet molding compound is made from chopped glass strands sandwiched between two layers of film onto which you have a resin paste that has already been applied. The prepreg passes through a compaction system that ensures complete strand impregnation before being wound into the rolls. So really robust ideas here on how to manufacture composites. Compression molded parts may contain a wide variety of defects. Porosity is one of them. It can result in internal voids, surface pits, surface irregularities. You could have air entrapment of other gases in the molded part, causing a potential failure scenario. Very important consideration. You can have blisters that form, interlaminar cracks that form, and then you can have other issues associated with fiber orientation, like cavity edges, short fibers, things like that. Advantage of this is easy to trim, high production rate, low cost, complex shapes can be done, good surface finish, and good consolidation. Disadvantages here is that you need a lot of money to buy the autoclave. The molds and tools are expensive, and you have a limited shelf time for the customers that need them. And finally, a few more things to touch on. Here, I'm just showing you really quickly the production volume for compression molding, injection molding, and so you may have some benefits in other areas, not as good. And this is 5 categories being looked at, for example. Summary of composite usage. You have carbon epoxies used in a lot of structural applications, trusses, pressure vessels, optical benches, racks, used a lot in aerospace applications. Glass epoxies are used in pressure vessels or a sacrificial layer as a protective cover of some kind that's bonded onto the real composite. Kevlar epoxies can be used for impact damage resistance, has been used in pressure vessels and small size rocket motors, and has low compressive strength. So keep that in mind as you work it. Kevlar, you have fiber reinforced thermoplastics, excellent damage tolerance, good replayability, and also lower structural performance thermosets. And yeah, so those are the ones I wanted to cover. And then here's a summary of composite manufacturing we talked about. I won't go through every single one of them because we covered them to some extent. But yeah, just keep in mind that there's a distinction between if somebody say, okay, come over, I'm going to make you eggs. Well, you don't know if it was made in America. None of that stuff is known to anybody. So all the time. Summary of composite manufacturing. Again, filament winding, the kinds of materials you could use. Carbon, epoxy is one of them, graphite epoxy, Kevlar, and things like that. So yeah, it shows you the common application, structural rocket motors for the filament winding in these materials. That makes sense. And what typical tooling you need. And so I hope you spend some time looking at this by pausing or reviewing later because I don't want to go into every single cell here. I think what I want to make sure is that you've kind of studied these aspects very well. Hand layup, mechanized tape layup, fully automatic tape layup, right? So good things there. And material specifications, we need to look at the supplier qualification. We need to look at the fiber requirements, the prepreg requirements, and the incoming and receiving. So when you receive material, you can check it. Somebody had a question last week whether that is done, and the answer is yes. You have process specifications like storage and handling, cure cycle, layup and bagging, process control, quality control, post-process quality control, and acceptable anomalies being resolved. Okay, with that said, I appreciate your time.